title of the talk is Reducing the Cost of Marine Renewables via Advanced Structural Materials, and this project essentially aims to deploy the most cost-effective materials for tidal turbines. We're also considering things like bearings for wave energy conversion as part of this project, and looking at the tribal corrosion resistance. Now, we've got 5 groups from various universities around the UK, ourselves in Strathclyde, Newcastle and Southampton. And what has been nice about this project is that with regard to Southampton and Strathclyde, we're 2 tribology groups interacting with 2 energy groups, and it's made for great synergy between the people involved. So the aims of the project were to develop and test advanced materials to improve the tribological resistance of tidal turbines. We're looking at loading impacts on blade structures and the mechanisms on the blades. We're also considering the tribal corrosion evaluation of the materials degradation, and then modelling the degradation and then testing in marine environments. So we're attacking the situation, going through the various steps, testing in the laboratory, developing models, and then ramping up the situation to where we're actually testing the material in the real environment. So just to talk about some of the tribological challenges, and this meeting last year we went through some of these issues. We have erosion is a major problem, and we had some very interesting talks this morning on sediment deposition mapping, and also the sort of scarring, the bed scarring, the last talk before lunch. So erosion is a major problem. It can be caused by solid particles. We can also have cavitation erosion, where erosion results from the formation and collapse of bubbles under pressure. The situation with erosion is that it can actually assist in chemical degradation. It can enhance chemical degradation, and chemical degradation can also enhance or impede erosion. It's rather a complex situation. And one of the things that occurred to us before we started this project was that erosion corrosion of metallic materials is well characterised as an enormous literature in that area, but for polymer-based composites, the area was a little bit unknown. There's been very little work done on tribochemical evaluation of polymer-based materials, polymer-based composites, and these are the kind of surprising results that have emerged from this project. This is the test rig. It's a slurry. This is one of our test rigs in the erosion corrosion. It's a slurry pot. It's essentially we're rotating the specimens in a slurry of particles. We can vary the particle concentration and the impact angle of the. We can vary the impact angle of the specimens also. And we've been testing in distilled water, and we've also been testing in seawater. Now, these are the results that we've got from the initial testing in the erosion corrosion environment. What we're finding is that in salt solution only we're getting weight gain, and this is for fine sand. And then as we add salt to at least if we look at the pure water situation, we get something like this. We get some mass loss. And then if we add salt to the solution, we get very significant mass loss. And this is for our composites, our polymer-based composites, materials that we didn't think we would see an effect of salt on the surface, because there wouldn't be a sort of a chemical attack on the surface. Now the situation is more severe, as you'd expect, with medium sand particles. And we're finding that we get similar kind of patterns, in the sense that with the salt in the salt in the solution, we're getting much higher mass loss than just in the distilled water. Okay, So in the, what we can see now, this under this some slight variation here by comparison to here, but that is a characteristic result in erosion, corrosion, degradation, depending on the actual mechanism that is occurring on the surface. And certainly on on composite-based materials, you will have mechanistic changes with the changes in the impacts or the size of the impacting particle. Now, one of the things we do in tribal corrosion, how am I doing for time, Karen? Yes. One of the things in tribal corrosion that we like to measure is the synergistic effect. That is the effect of the enhancement or otherwise of the surface due to the chemical degradation. What we did here is we actually subtracted the results from the material exposed to the seawater only, and then from the situation where we had sand impacting the surface in the seawater conditions. We get very significant synergistic effects on the surface, identifying that the salt is having some effect on the mechanical attack on the surface. Now, what do the micrographs tell us? That's just with water and sand. You see some indentation marks over the surface here. But if we add salt to the system in the saltwater conditions, you can see here extensive cracking here on the surface. Okay, so we're getting a sort of a mechanically assisted cracking on the surface. Now, if we were to talk about a metallic material like a steel, we'd be talking about a stress corrosion cracking environment where we get a mechanically assisted cracking process which propagates due to the sort of the chemical degradation at the crack tip and assisted by stress. But what we didn't see and that is essentially an electrochemical mechanism, what we didn't expect to see is the same thing or something very analogous happening on the composite. Okay, so what we've been doing is we've been generating erosion maps to describe the behaviour, and this is essentially the situation just in seawater. We have just, these are sort of rates of mass loss. For seawater, by comparison to particles in seawater, you can see much higher wastage rates, the attack being highest at intermediate impact angles. And there's a reason for that. It's a sort of one of these characteristic results for erosion literature where you get impact angle dependence. What we can also do is actually generate these maps based on mechanistic changes. So we can identify mechanistic changes, whether we have erosion of the matrix material or of the reinforcement material in the composite. Now, the next phase of the work was to model the impacts on the blade structure, and we've been doing that. The ESRO team in Strathclyde have been doing this with Newcastle University, inputting some of their material data into the model, and then using a sort of a collaboration between the two groups to actually assess a range of parameters on the blade performance. We've also been testing various materials, various composites structures in Newcastle. And the other work that Newcastle has been doing is to look at the effect of reinforcing with carbon versus no carbon. I can see here, looking at the endurance limits, and they've also tested seawater in air. We can see changes in seawater, sort of deterioration with seawater, and also with the carbon we get a change also, as you would expect, as the matrix is stiffer. So I'd like to hand over to Tom Blackmore now, my colleague from Southampton, who will be talking about the testing that we're doing in the real-life environments. Okay.
Cheers. Hi. So this is following on from some experiments last year that we did at EFRAMAT. So we used a static grid to generate turbulence in the Flume. and then we characterise the flow using the LDA that you saw in the previous presentation, and then we put the turbine in these different turbulent flows to measure what happened to the turbine performance. So we found that turbulence intensity has the effect of reducing both the power coefficient and thrust coefficient of the turbine. But the integral length scale, so the size of these turbulent eddies, seem to have a different effect, and they actually increase the power coefficient and thrust coefficient. And the overall variation is in the range of 10% variation in CP and CT. This also has a significant effect on the fatigue fluctuations on the blades. So these two plots I'm showing in the bottom right-hand side here are the fluctuations in force on the rotor and on the blade root bending moment. So the left plot shown here is the thrust, and then this is the torque, and we can see there's a linear relationship between what's going on with fluctuations in rotor and also with fluctuations on the blade. So we've proposed the possibility of monitoring the fatigue loads that the blade is seeing by monitoring the power output of the turbine, and this would remove the need to actually instrument the blades themselves. So the second part that we've been doing is a deployment of the same turbine that was used in the Erosion Flume in the River Itchen in Southampton Water. We've done 2 deployments this year, and this enables us to compare the blade loads with what we had measured previously in the Flume. So even with high levels of turbulence in the Flume at Erosion, the levels of force fluctuation in the River Itchen site were much, much greater. So you can see this figure here is showing the rotor torque, and it's showing it with blade position from 0 to 360. So the red data is from the River Itchen, and the blue data is from the Flume. So you can see there's a huge difference in variation in force. I've shown that here as a histogram, and we can see the blue is from Erosion, so we've got a very sort of close spike in forces, and it's very uniform, whereas when we put the turbine into the river, we get a very skewed profile, and we get these much larger forces than what we had in the laboratory. This is ongoing work, looking at ways of making further comparisons, but it seems that from operating in a real site, there's a huge variation compared to what you'd get from a Flume, even with added turbulence in the Flume. So, I'll hand back to Margaret.
Okay, so we've been looking at the effect of the tribological situation, and including erosion, corrosion, fatigue, and we've been considering the synergy between mechanical and chemical degradation, modelling the mechanistic changes on the surface, and then the later stage of the project is the testing in the marine environment. What is encouraging from what I've seen this morning is there are a lot of data out there. There are a number of talks this morning where I could see that we can use these kinds of the parameters, the mapping of these kinds of parameters like sediment deposits and salinity. We can use those kinds of parameters to inform our lab testing and also the ongoing model development. Thank you for your attention.
This production is brought to you by the University of Edinburgh.